Now we come to 1, 2, and 3-dimensional flows. A fluid flow, when a fluid is flowing and we need to consider it, analyze it in mathematical terms, we need to see whether it is one-dimensional, two-dimensional, or three-dimensional. That is, its parameters are changing or moving in all these directions. So in the many times, if they are moving in a limited direction or in one of the direction instead of three, then that makes it that much simpler and easier to solve the problem, such a fluid flow conditions, and to predict the motion. But if it is two-dimensional or three-dimensional, then it becomes that much complicated. But then there are several techniques to simplify them, and still they can be solved. So we shall consider as they will come. At the moment, we are just introducing or describing what kind of flows these three can be and how do we address them. A flow field is best characterized by velocity distribution, and thus a flow is said to be 1, 2, or 3-dimensional if the flow velocity varies in 1, 2, or 3 primary directions or dimensions. So velocity is the main player in a fluid flow, the velocity vector, and it has 3 components, x, y, z, as you know. So a typical fluid flow involves a 3-dimensional geometry, and the velocity may vary in all 3 dimensions, rendering the flow 3-dimensional. The velocity vector will have its component in x, y, and z direction if we are considering rectangular coordinates, or if we are considering cylindrical coordinates. Let's say the fluid is flowing in a pipe, for example, then the geometry is cylindrical, then it's better, more convenient and easier to solve the fluid flow situation in a cylindrical polar coordinates. So the rectangular coordinates are considered as x, y, z, as you know, and cylindrical are u and z, or similar terminology that we use. However, the variation of the velocity in certain directions can be small relative to the variation in other direction. And therefore, for example, if the velocity vector is dominating, let's say in x direction, then the fluid flow can be ignored in y and z directions, or only in r direction, and it can be ignored in u and z directions. It all depends on the flow situation, and therefore we consider it. For example, here is a fluid flow situation. We try to see how it is moving, and then when we are modeling the equations for this problem and trying to solve the situation with appropriate boundary conditions, then you can see how the fluid is developing. Here is a pipe that is attached to a fluid coming from the left hand side, as you see, and it's going to in the right hand direction. As the flow is introduced into the pipe, then you can see, and let's say because it is cylindrical, therefore we are choosing its motion as x, y, and z, r, y, and z. So here the 2 dimensions that are important are shown to you. R is the radius that belongs to that's particular to the cylinder, and z is its axial direction. So you can see as the flow is moving into the pipe, in the beginning it's uniform, then viscosity is taking its effect. We shall be talking about viscosity a little later. And therefore, close to the boundary, the fluid sticks to the boundary, the solid boundary, and therefore its speed there is 0. And as the fluid moves away from the boundary, it picks up some speed and it gets its maximum value where r is equal to 0. And therefore, as you may see in the picture, the middle point is smooth, but the point close to the boundary is not that smooth, and it's taking point shape from 0 onwards. After a while, if we let the fluid flow for a while, then it takes a position. As you can see, step by step, the picture is trying to show its movement and its profile. Then you see that as after a while, it takes a uniform shape. The last two pictures are almost showing identical conditions, and that we can consider for the sake of solution of a problem and analysis of a fluid flow as a steady condition. And we are going to solve it, attack it that way. So, and we call it as fully fluid profile, velocity profile. You can look at it. It has a maximum value at r equal to 0. It has a 0 value at the boundary where the radius is equal to the value r. R may be equal to a there, if a is the radius. But in between it is changing. Close to the boundary, the velocity is very small. As you move towards the central point where r is 0, then it is having the maximum value and it remains the same onwards. So this was just a description of 1 to 3 dimension in cylindrical motion.